Section 6.4, Exponential and Logarithmic Equations. In this section, we'll see how to solve exponential equations using the exponential equality property. We're going to talk about how to solve exponential equations with base 10 or base e, and how to solve exponential equations graphically. Then we'll talk about some fundamental properties of logarithms, and how we can solve exponential equations using properties of logarithms. Then we'll talk about solving logarithmic equations and solving literal equations, formulas involving exponentials and logarithms. We'll discuss the change of base formula and some applications. So first, solving exponential equations with the exponential equality property. This property states that if the base is positive and not 1, if we have an equation where we have the same base, then we must have the same exponents. If b raised to the m power is equal to b raised to the n power, then m must be equal to n. So for example, we're asked to solve 2 to the x is equal to 2 to the 4x plus 6. Since we have the same base, then the exponents must be equivalent. So then we can write x must equal 4x plus 6. And we can easily solve this equation. Subtracting 4x, negative 3x equals 6, and dividing by negative 3, x equals negative 2. Now if we look at the next exercise, we have 3 to the 2x minus 11 is equal to 27 to the 3x plus 1. We cannot immediately set the exponents equal because we don't have the same base. So we have to use a little bit of trickery here. Notice that 27 is the same as 3 to the third. So I have 3 to the 2x minus 11 is equal to 3 to the third to the 3x plus 1. Now I'm going to use a property of exponents. When you raise a power to a power, which is what I have on the right hand side, I have 3 to the third to the 3x plus 1. When I raise a power to a power, you multiply exponents. So that's 3 raised to the 3 times 3x plus 1. So then we have 3 to the 2x minus 11 is equal to 3 to the, using the distributive property, 9x plus 3. So now since I have the same base, I can equate the exponents. 2x minus 11 is 9x plus 3. Subtracting 9x from both sides and adding 11 to both sides. Negative 7x equals 14, and dividing by 7, negative 7, x is again negative 2. Alright, and that's just coincidence that we get negative 2 for both of those equations. Solving exponential equations with base 10 or base e. To solve these equations, what we will do is we'll first isolate the power. So that's the term containing the variable exponent. Then we'll take the equation and convert it to a logarithmic form and solve for the variable. So let's consider this example. We're asked to solve 3 plus 5 times 10 to the x minus 1 is equal to 7. Now, be careful here. If you write this, 3 plus 50 to the x minus 1 equals 7, it's immediately wrong, because you've gone against the order of operations. You've taken care of a multiplication before dealing with the exponent. We cannot do this. Alright, so what I need to do is I need to isolate this 10 to the x minus 1. What's happening to it? There's a multiplication by 5 and an addition of 3. We undo those in the other order. I will subtract 3 first. 5 times 10 to the x minus 1 is equal to 4. I'll divide by 5. 10 to the x minus 1 is equal to, I'm just going to leave it as 4/5. You can write it as a decimal, but you don't want to do any approximating. I've now isolated the power. I've isolated the exponential. Now I'm going to convert to logarithmic form. Since this is base 10, I can use the common logarithm. So then I would have x minus 1 is equal to the log of 4/5. Adding 1 to both sides, x is equal to 1 plus the log of 4/5. That's an exact value. We can use our calculator to find an approximation. 1 plus the log of 4/5 is approximately 0.9031. X is approximately 0.9031. You may be asked to solve exactly and solve approximately. So you need to be able to write this answer in either form. Alright, the second example, we have 25e to the 2x minus 3 is equal to 9. I want to isolate e to the 2x minus 3. I will divide both sides by 25. E to the 2x minus 3 is equal to 9/25. Now again, you can write an exact value for that. I'm just going to leave it alone as 9/25. Turn this to a logarithmic form. Since it's base e, we can use the natural logarithm. 2x minus 3 is equal to the natural log of 9/25. Now I'll solve for x. I'll add 3 and I'll divide by 2. So x is equal to 3 plus the natural log of 9/25, all divided by 2. Let me approximate that. So now if I'm thinking on the calculator, I'm going to need parentheses around the entire numerator before I divide by 2. So parentheses, 3 plus natural log 9/25. I'm going to close the natural log, close the numerator, and divide by 2. 0.9892. Alright, in the second exercise here, 7 times the quantity 1.2 minus 10 to the 0.25x is equal to 0.63. I want to isolate 10 to the 0.25x. Alright, so it's being subtracted from 1.2 and then multiplied by 7 and we get 0.63. So I will first divide by 7. Yielding 1.2 minus 10 to the 0.25x equals, now that's an exact decimal, that's 0.09. I'll subtract the 1.2 from both sides. Let's see, 0.09 minus 1.2 is negative 1.11. I'll divide both sides by the negative 1. 10 raised to the 10 raised to the 0.25x is equal to 1.11. I will convert this to the logarithmic form. 0.25x is equal to the common log of 1.11. And to finally isolate x, I'll divide by 0.25. X equals the log of 1.11 divided by 0.25. And I'll approximate it. .1813. X is approximately 0.1813. solve graphically, we have this equation involving an exponent, right? 2 to the 2x minus 7. Well, to solve graphically, just as we've done other equations, I'll treat the left-hand side as my y1 and the right-hand side as my y2. I'll graph them both in a window and see where they intersect. Let's clear up some old stuff here. y1, 2 exponent quantity 2x minus 7, close quantity, subtract 27. y2 is 25 raised to the 1/2. Now, of course, if you recognize that as just being the square root of 25, you could just write that y2 equals 5. All right, and we'll graph this. Let me check my window. Let's start in a standard window. So let me hit zoom 6 and start in the standard window. And I do see a point of intersection. Now, we have this 2 to the 2x minus 7, so I should be expecting an increasing function. Let's make sure that there's no other intersections. So let me change the window. I'm going to adjust the y minimum to negative 30. And let's see if that gives us a better picture. So we see the exponential function and y equals 5. This, right, 25 to the 1/2. Let's calculate that point of intersection. I'll move my cursor to the right to get close to the point. Too far. Hit enter slowly 3 times. And it's at exactly x equals 6. So the solution of the equation is x equals 6. And we can verify this. Let's see. Well, let's see. 2 to the 2 times 6 minus 7 minus 27 equals 25 to the 1/2. That's the square root of 25. So that's 2 to the 12 minus 7. That's 2 to the 5th minus 27. 2 to the 5th is 2, 4, 8, 16, 32. 32 minus 27 does equal 5. So it works. X equals 6. Fundamental properties of logarithms. Alright, from earlier ideas, we know that the log base b of 1 is 0. For example, the log base 5 of 1. 5 to the what power gives us 1? Right? Well, 5 to the 0 is 1, so the log base 5 of 1 is 0. The log base b of b is 1. That should seem reasonable. Log base b of b to the x is x, and b to the log base b of x is x. And these are inverse properties. Now we have some additional properties that we can use in helping us solve equations. For positive real numbers m and n and any real number k, the log base b of a product, if I'm taking the logarithm of a product of numbers, I can write that as a sum of logarithms. The log base b of m times n is the log base b of m plus the log base b of n. Similarly, if we have a division, log base b of m divided by n is the log base b of m divided by, subtract the log base b of n. And we have a power property for logarithms. The log base b of m to the k is k times the log base b of m. And these are important properties in helping us solve equations. So let's see some examples of how we can use these properties. We're asked to write as a single logarithm, and here I have 4 times the log base 6 of x minus 1/2 times the log base 6 of y. So since they're of the same base, I can use properties to rewrite these as a single logarithm. First thing I'm going to do is use the power property. So here I have k times a logarithm, right? 4 times the log base 6 of x. I can take this coefficient and put it as an exponent on on the x. So I have the log base 6 of x to the 4th minus the log base 6 of y to the 1/2. Right, I use the same idea here. Now, since I have a subtraction, I can write this as a single logarithm, base 6, of a quotient, x to the 4th over y to the 1/2. Now, sometimes you might see this, log base 6 of x to the 4th over the square root of y. Right, since raising to the 1/2 power is the same as finding the square root. Here's another example. Log of y plus 3 log of z minus 1/5 log x. All right. Again, I'm going to use this power property. I have this 3 log z. I can write that as the log of z cubed. 1/5 log x. Log of x to the 1/5. Log y plus log z cubed minus log z to the 1/5. I'm sorry, that should be an x to the 1/5. Now, since I have a sum here, I can write these two logarithms as a logarithm of a single product, y times z cubed. And now, since I have a difference of logarithms, I can write a quotient of a logarithm of a single quotient, where I'd have y z cubed in the numerator and x to the 1/5 in the denominator. Let's use the ideas in the other direction. Let's expand in terms of simpler logarithms. Here we have the natural log of the 7th root of x times y to the 5th. The first thing that I can do is rewrite this product, this natural logarithm of a product. I can write the natural logarithm of this product as a sum of two natural logarithms. So I'd have the natural logarithm of the 7th root of x plus the natural logarithm of y to the 5th. Now recall that the 7th root of x is the same as x to the 1/7 power. And so now, using the power property, I can bring each of these exponents out front of the logarithm as coefficients. 1/7 natural log x plus 5 natural log y. Let's look at the second example. Write in terms of simpler logarithms the log of 3y over x plus 2 cubed. First thing that I'll do is I have this division. All right, so I can take this division and I can write it as I can get a difference, a subtraction. So I'd have the log of 3y minus the log of x plus 2 cubed. Now, I still have a product here I can take care of. 3y is the same as 3 times y. So that becomes a sum of logarithms. Log 3 plus log y minus still log of x plus 2 cubed. Now, since I have this x plus 2 cubed, I can take this 3 and bring it as a coefficient on this logarithm. So I have log 3 plus log y minus 3 log of x plus 2. Now, I cannot do anything with the log of x plus 2. It is not a product or a quotient or an exponential. So I have to leave that alone. And so there's the expression in terms of simpler logarithms. Now that we have the properties of logarithms, in particular the power property of logarithms, we can solve general exponential equations. To do this, we isolate the power on one side of the equation, and then we take the logarithm of both sides. Usually we're going to use base 10 or base e. We're going to apply the power property of logarithms to simplify, and then we'll isolate the variable. So let's see how we do this. Negative 2 minus 4 to the 2x equals negative 13. Alright, so I want to isolate this 4 to the 2x. I will add 2 to both sides. So then the opposite of 4 to the 2x is equal to negative 11. I'll divide through by the negative 1. 4 to the 2x equals 11. Now, I'll take the log of both sides. I'm going to use the common logarithm, the base 10 logarithm. So, the log of 4 to the 2x is equal to the log of 11. Now, using our property, our exponent property, our power property of logarithms, the log of 4 to the 2x, I can take this 2x and bring it down in front of the logarithm as a coefficient. So that gives me 2x times the log of 4 is equal to the log of 11. Now notice that that's just the same as 2 times log 4 times x is equal to log 11. And so that's just a number times x equals log 11. So x is equal to log of 11 over 2 times the log of 4. And now we can approximate that if we wish. Log of 11, close it off, divide by the quantity 2 times the log of 4. Close the log, close the denominator. So about 0.8649. Alright, here's a couple more examples. Let's see, we have negative 9 is equal to 7 minus 8 raised to the times 3 to the 4x plus 1 power. First thing I would do is subtract the 7 from both sides. So then negative 16 is negative 8 by 3 to the 4x plus 1. I'll divide through by negative 8 to isolate the exponential. 2 equals 3 to the 4x plus 1. Now, like I did in the previous exercise, I'm going to apply the common logarithm to both sides. Log 2 is equal to log of 3 to the 4x plus 1. Now I will use the power property to bring this 4x plus 1 down as a coefficient. Log 2 would equal 4x plus 1 times the log of 3. Now it's multiplying. So now to solve for 4, we need to solve for x. Well, one approach would be, let's divide by log 3. So then log 2 over log 3 is 4x plus 1. Now to isolate x, I would subtract 1 and divide by 4. So then x would equal log 2 over log 3, subtract 1, divide by 4. And we can approximate that. Let's see, the entire numerator is in parentheses. Then I have log of 2 divided by log of 3. And then I'm going to subtract 1, close it off, divide by 4. So negative 0.0923. Alright, let's look at the second example. I have negative, not negative, but the opposite of 12 to the negative 2x minus 3 plus 9 is equal to negative 1. Let me subtract 9 from both sides. The opposite of 12 to the negative 2x minus 3 is negative 10. I'll divide by negative 1. 12 to the negative 2x minus 3 is 10. I apply the common log to both sides. Now, notice that the log of 10 is just 1, isn't it? Alright, that's the common logarithm. The log of 10 is 1. Using my power property, I can write this as negative 2x minus 3 times the log of 12 equals 1. Again, the log of 10 is 1. Now to solve for x, first thing I'll do is divide by log 12. So negative 2x minus 3 is 1 over the log of 12. And to isolate x, I would add 3 and divide by negative 2. So x is 1 over the log of 12, add 3, divide that whole thing by negative 2. 1 over, let's see, I need parentheses for the numerator. 1 over the log of 12. I'd have to add 3 to that and divide that whole thing by negative 2. So negative 1.9633. Solving logarithmic equations. Alright, to solve logarithmic equations, what we're going to do is we're going to isolate the the logarithmic expression on one side of the equation. If necessary, we may need to apply properties of logarithms to combine all the logarithms to a single logarithm. We're going to then convert this to an exponential form, solve for the variables, and what we must be sure to do when we're solving logarithmic equations is we must check the solutions. So let's solve the equation. 6 plus the natural log of x to the fifth is equal to 8. Alright, so I want to isolate the logarithm. I'll subtract 6 from both sides. So then the natural log of x to the fifth is equal to 2. Now I could write that as 5 times the natural log of x equals 2, but we don't have to. Let me convert this to an exponential form, since now I have the natural log x isolated. So then x to the fifth is equal to e squared. And then applying our property to solve for x, I would raise both sides to the 1/5 power. So then I would have x to the fifth to the 1/5 equals e to the second to the 1/5. And so then using properties of exponents, then x would equal e to the 2/5 power. And we can approximate that if we wish. .4918. Now let's check our work with this. I'm going to use the exact form. So if I have 6 plus the natural log of e to the 2/5 to the 5th power, is this equal to 8? E to the 2/5 to the 5th, using our properties for exponents, that's e to the second. So that's 6 plus the natural log of e to the second. The natural log of e to the second is 2, so that's 6 plus 2, which is 8. Alright, so I'm confident in my solution. Solve log of x plus log of x minus 3 is equal to 1. Using a property of exponents, I can write this as a single logarithm. of x times x minus 3. So that's the log of x squared minus 3x. Now, let me turn this into an exponential form. Since this is the common logarithm, that means we have base 10. So then x squared minus 3x is equal to 10 to the first power. So x squared minus 3x is equal to 10. This is quadratic, so I can solve it. I'll move the 10 to the other side. And I think this factors as x plus 2 by x minus 5. So then x plus 2 equals 0, x minus 5 equals 0. So then x equals negative 2, x equals 5. So we appear to have two solutions to this equation. But now we have to check. We always have to be careful about when we have this situation where we're solving logarithmic equations. Sometimes the solutions are outside of the domain of the expressions. So notice that if x is negative 2, can we find its logarithm? What is the log of negative 2? Non-real. Same thing here. Negative 2 minus 3. Log of negative 5. Non-real. X equals negative 2 is not a solution of the original equation. Let's do a quick check on x equals 5. Log of 5. Right, we would have the log of 5 plus the log of 5 minus 3 is 2. Log of 5 plus log of 2 is the log of 5 times 2. That's the log of 10, which is 1. X equals 5 is a solution. Let's look at another example. Log base 2 of 1 plus 8x minus the log base 2 of 2x minus 1 equals 3. Alright, so since we have a subtraction here, I can write a quotient. Log base 2 of 1 plus 8x over 2x minus 1 equals 3. Let me convert this to an exponential form. 1 plus 8x over 2x minus 1 equals 2 to the third power. So 1 plus 8x over 2x minus 1 equals 8. Alright, now, this is basically a proportion. Let me multiply through both sides of the equation by 2x minus 1. So then 1 plus 8x equals 16x minus 8. Subtract the 16x from both sides, negative 8x equals, subtracting 1 from both sides, negative 9. X equals 9/8. Alright, let's do a quick check of this solution. Log base 2 of 1 plus 8 times 9/8. That's the log base 2 of 1 plus 8 times 9/8 is 9, minus the log base 2 of 2x, that's 18 over 8 minus 1. 18 over 8 minus 8 over 8 is 10 over 8. So that's the log base 2 of 10 minus the log base 2 of 10 over 8. I can write that as the single logarithm. Oh, and notice that there's no negatives, as the arguments for the logarithm, so we can be fairly confident right away. But just to finish it out, we'd have the log base 2 of 10 over 10/8, and that's the log base 2 of 8, which is in fact 3. So it does work. X is equal to 9/8. Solving literal equations. So if we have an equation that involves various variables and we wish to solve for one of them, we can use the same techniques. We just have to be more careful. Alright, so we have y equals c over 1 plus a times e to the negative bt. We're asked to solve this for t. Alright, so one approach that we could do is, well, let's get rid of the fraction. So let me multiply both sides by 1 plus a e to the negative bt. So then I would have 1 plus a e to the negative bt times y equals c. Now I'll divide through by y. So I'd have 1 plus a e to the negative bt is equal to c over y. Alright, now we're almost there, really. Because now I can easily get the exponential by itself, and then I can apply the logarithm. Alright, I'll subtract 1 from both sides. A e to the negative bt is equal to c over y minus 1. I'll divide through by the a. E to the negative bt is equal to c over y minus 1 over a. Now I will apply the logarithm to both sides. Since it's a base e, I'll apply the natural logarithm, or I'll just convert this to a logarithmic form. Negative bt is equal to the natural log of c over y minus 1 over a. And finally, to isolate the t, I'll divide through by negative b. T is equal to natural log c over y minus 1 over a, and that whole thing's being divided by negative b. So what if we wanted to evaluate the log base 7 of 36? Well, let's call it some number, x. So let's say that x is equal to the log base 7 of 36. Well, I can convert this to an exponential form, and so then 7 to the x would equal 36. Now I can solve this by using the common logarithm. The log of 7 to the x would equal the log of 36. Using our power property, I can write the left-hand side as x times the log of 7 is still equal to the log of 36. And so then x would equal the log of 36 over the log of 7. Now, I can use my calculator to approximate this, and so then, let's see, log of 36 divided by log of 7 is about 1.8416. So, in general, if we want to find the log, a general base of some number, the log base b of n. Now I chose to use the common logarithm, but I could have used any number greater than 1. I could have used any base and done something similar. The log base b of n is equal to the log base a of n over the log base a of b. Our common, what we commonly do is use either the common log or the natural log. So usually what we do is we say that the log base b of n is log n over log b, or that the log base b of n is the natural log of n over the natural log of b. This is known as the change of base formula. So how could I solve 3 to the x is equal to 30? If I change this to logarithmic form, then x is equal to the log base 3 of 30. Well, then that's the same as the log of 30 over the log of 3. And we can use the calculator to approximate this. And so it's approximately 3.0959. 0959. What if we wanted to graph a logarithmic function on the calculator, but it wasn't the common log or the natural log? Use the change of base. If y is equal to the log base 7 of 2x, that's the same as the common log of 2x over the common log of 7. And so now on the calculator, let me clear out this old stuff. I would type in log of 2x, close that off, divide by the log of 7. Close that off. And let me just go to the standard window, and we get a graph. All right. So you can use the change of base formula even though there isn't certain, we only have two logarithms to work with on this calculator, the common log and the natural log. Other calculators can deal with general logarithms. This one, the one that I have here, that I'm demonstrating with, only has the common log and the natural log, so I have to use the change of base formula to put it in those terms. Alright, so now let's look at some applications. Here's one. According to the Motion Picture Association of America, the number of digital 3D screens worldwide has increased dramatically during the last years. The function p of t equals 89.371 times 3.2 to the t models the number of digital 3D screens worldwide for t number of years after 2005. Using this model, estimate when the number of digital 3D screens reached approximately 9,000. So we want to solve where is p of t equal to 9,000. So where is 89.371 by 3.2 to the t equal to 9,000? Well, we know how to solve this. I'm going to isolate the exponential. I'll divide through by 89.371. 3.2 to the t is equal to 9,000 over 89.371. Now, I'm not going to calculate this yet, because it's probably going to be a nasty decimal number, and I don't want to round too early. Don't round until the end. Now, I'm going to apply the logarithm to both sides, and use the property of logarithms. T, so I can write t log 3.2 is equal to log of 9,000 over 89.371. Solving for t, t is equal to log of 9,000 over 89.371 over 3.2. I'm sorry, log of 3.2. Let's approximate that. So t is approximately 3.96. So that's about 4. So in 2009, the number of digital 3D screens reached 9,000. Here's another application. The number of prohibited firearms intercepted by the Transportation Security Agency at U.S. airport screenings since 2005 can be modeled by f of x is equal to 2,391.893 minus 931.691 natural log of x, where x represents the number of years since 2005. Use the model to determine when the TSA intercepted approximately 900 firearms. So we want to solve f of x is equal to 900. So then we'd have 2,391.893 minus 931.691 natural log x equals 900. I'll subtract the 2,391.893. 900 minus 2,391.893. Negative 1491. So, negative 931.691 natural log x equals negative 1,491.893. I will isolate the natural log of x by dividing. So the natural log of x would be, and a negative divided by a negative is positive, 1,491.893 over 931.691. So that's the natural log. I want to solve for x. I'll convert this to exponential form. So then x would equal e raised to the 1,491.893 over 931.691. Now I'll approximate that. E to the 1,491.893 over 931.691. So x is approximately 4.96. And so this is number of years since 2005. So about 5 years later, in 2010, the TSA intercepted about 900 prohibited firearms. The population of Braddock, Pennsylvania was 4,468 in 1990. Braddock has experienced a continuous annual decline of approximately 3.5% in the population rate since 1990. Write a natural exponential function p of t that models Braddock's population since 1990, where t represents the number of years since 1990. Since we are told that we have a continuous annual decline of approximately 3.5%, that tells me that I can use an exponential model with the base e and with k equal to negative 0.035. So my natural exponential function would be p of t equals 4,468, that's the initial value, e to the negative 0.035 t. Assuming the given decline rate continues, when will the population drop below 2,000? Well then, we would have p. We need to solve where is p of t. Let's find when p of t equals 2,000 first. So we'd have 4,468 e to the negative 0.035 t equals 2,000. Let's divide through by 4,468. So e to the negative 0.035 t is equal to 2,000 over 4,468. I'll convert this to a logarithmic form by applying the natural log. So then I would have negative 0.035 t is equal to the natural log of 2,000 over 4,468. And I will then divide by negative 0.035. So then t would equal the natural log of 2,000 over 4,468 divided by negative 0.035. We calculate that. 22.96, so t is approximately 23. Conclusion: 23 years since 1990. So in 2013, the population of Braddock, Pennsylvania, will drop below 4,468. So where does this number e come from? One approach to finding the value of e is to talk about compound interest. Now, we haven't discussed compound interest yet, and we'll do that in section 6.5. Compound interest tells us that the interest that you earn is based on the principal times 1 plus the interest rate as a decimal over the number of compoundings per year raised to the number of compoundings times the number of years. So, and we'll go into more detail with this, but in the next section. But let's just look at this idea. What is the value of an investment of $1 that earns 100% interest after 1 year, if it is compounded however many times per year? Alright, so investment of $1, P equals 1, that earns 100% interest, R equals 1. After 1 year, T equals 1. So our interest now is given by 1 times 1 plus R over N to the N times 1. Simplifying this, we would have 1 plus, well, wait, R is 1, isn't it? We'd have 1 plus 1 over N to the N. Now, I'm going to see what happens if it's 10 times per year, 100 times per year, and a very large number of times per year. I'm going to use the calculator for this. So I'm going to set up a formula on my y equals screen. It's going to be 1 plus 1 over x to the x. All right, my calculator likes x instead of n. Now I'm going to use a table. So let me set up my table so that it's on ask for the independent line. So now, if I have 1 compounding per year, this is simple interest. I should get $2 back at the end. I invested $1, I get $2. What if it's 10 times per year? Yeah, get better. $2.59 after the year's over. 100 times per year? 2.7048. So it's more, I get a better amount of money, but it's not as significant as, you know, going from 1 to 10. What about 1,000? Let's see, 2.7169. How about 10,000? 2.71. Hey, that sounds familiar, doesn't it? 2.718. Well, that's pretty darn close to E, isn't it? Let's throw another 0 on there. 10,000, 100,000. 2.71826. The approximation's even better. Alright, last one. Let's go to a million. If it's compounded 1,000,000 times per year, 2.71828. So that's all the way to 5 decimal places. So what happens to this value of the investment as the number of compoundings becomes very large? So here's what we would say. As n approaches infinity, as n becomes very large, the interest approaches, not the interest, but the value approaches e. And so here is a natural way to construct the number e using compound interest. A very simple case where we let the number of compoundings become very large. We'll go into more detail of compound interest in the next section. Alright, that concludes the presentation for 6.4.